So, thank you for the organisers for letting me speak. I'm Joe, working with Andy Taylor and Lucas Lombriser, who's over there at the University of Edinburgh. I'm doing my PhD on reconstructing Horndeski models from EFT. So I know a lot about EFT, so I won't go into the background so much. In fact, I'll go over this very quickly. But we know that there's a very large model space of dark energy and modified gravity models that have been imagined over the past 10 years or so in order to explain cosmic acceleration. And if you were to go through each of these models and compute the observational consequences, that would be challenging. And the effective field theory of dark energy, which we've all heard a lot about, is an efficient way to explore this parameter space, this model space. So this model space is large, even within Horndeski theory. You have 5 free functions. So firstly, we all know this, but when you add a scalar field into Einstein's gravity, and you want to construct the most general local Lorentz covariant 4-dimensional scalar tensor theory with second order equations of motion, you get Horndeski theory. It has potentially a number of motivations for more fundamental physics. This is what it looks like. It's a real mess. So you have 5 free functions, G2, G3, G4, and G5, all free functions about the scalar field, and X, the derivative of the scalar field. And you could compute for black hole solutions in Horndeski, and this is cosmological solutions. This is the full sort of covariant theory. It's a mess. So EFT.
Oh, yeah.
Well, we all know the background anyway, so hopefully it won't be too much missed on the video. Anyway, so EFT is an efficient approach to testing in a unified way the dynamics of the perturbations in Horndeski theory and cosmological scales. So you go into this ADM decomposition. The scalar field is just a function of time. For this talk, I'm going to choose a very particular foliation where you set the scalar field equal to time. In fact, that's quite important. And then you do this coordinate transformation, and your kinetic term just at first order in the perturbations becomes this. And then you can do this if you do this coordinate transformation in Horndeski, what you get out is an action order by order in the perturbations. This is sort of a background term and first order and then second order in the perturbations. So to build it up a little bit, you have sort of Einstein gravity with just this the ridge scalar here, and then you have a free function of time t here because you can break time diffeomorphism invariance keeping spatial diffeomorphisms when you're free to add in this extra function of time. If omega of t is 1, you get Einstein's gravity. You can add another function of time, lambda of t. If that is constant, you get lambda CDM. And you can build it up, some function of delta G naught, write down everything you can possibly write down consistent with the symmetries of your theory. If this gamma here is m star squared, that would be a quintessence model. And you can go up to second order. So with omega, lambda, gamma, these 3, and h of t, you have essentially 7 free functions that can describe Horndeski theory at the level of the background and linear perturbations. You have 2 background equations, which reduces the number of free functions to 5. So that's quite nice. So I think we've a lot of talk about this before. There's a much nicer basis in which this can be seen in terms of these alphas, which I won't. I think it's already been explained what they are. So essentially you have modified Planck mass, coupling between the metric and the scalar, kinetic energy of the scalar, and deviation of the speed of gravitational waves from the speed of light, alpha t. So you can fix your background expansion and look for probes of modified gravity and the perturbations in terms of the alphas.
There's just a linear transformation relating these EFT functions to this other basis. Quite often you see the alphas written in terms of these functions, but I think it's quite a nice exercise to do the inverse transformation by expressing these parameters in terms of the alphas, and you get some expressions like this, where this term here, which, if you remember, this is a specific form to describe Horndeski. If alpha t is equal to 0, then this term is equal to 0. Also, there's this omega, which was out in front of the Ricci scalar. That's both related to a modification of the Planck mass and the speed of gravitational waves. So there's kind of two things here. Lucas will talk a bit about that tomorrow in more detail, but it's quite a nice expression. And then we can do the same for all of them. Yeah. Okay, so to really get to the guts of it, the EFT functions are phenomenological. So in principle, you pick a parameterization of these EFT functions and compare them to data and constrain that. But is it possible, given constraints on these phenomenological EFT functions, what can we say about the theories that correspond to them? So there's some discussion on this morning. Normally you start from a particular covariant theory, compute the alphas associated with that covariant theory, and then plug it into high class or something to see what it does to the power spectrum. But is it possible to go from the EFT space back onto the space of sort of covariant, manifestly covariant theories? So this is what we've been working on. Can basically reconstruct the class of covariant Horndeski models. So that's probably a bit, Horndeski models that are equivalent only at the level of the background and linear perturbations. Of course, there's going to be a lot of degeneracy between the different theories. We've seen there can be sort of vector tensor theories that give rise to an alpha n, for example. But if we're asking the specific question of just Horndeski, what specific Horndeski model gives rise to the alpha m's? So I'm just going to show you. I'll do a sketch of the derivation of this, so try and convince you that it's correct. So this is essentially the result. So you have G2, G3, G4, G5. Each of these terms here are written in terms of the EFT parameters out here. So that's what I'm saying. If you give me a set of EFT parameters, you can plug this in and find, say, a potential, a Z, and a 2. So, this is sort of your K-essence term. And then this is everything that multiplies box phi. This is your G4. It's kind of what couples to the Einstein Ricci scalar, or the Ricci scalar. These delta G2s here essentially encode the degeneracy between different covariant theories that lead to the same theory at the level of the background and linear perturbations. If you can add on, I've defined these a couple of slides later on, but it's well defined that you can add these on such that your theory won't change at the level of the background and the perturbations. But you essentially add these on in such a way to move between different covariant theories. Okay, so just to show you in more detail what this is like. So you have U of phi, Z of phi, F of phi, C1 of phi. I should say, in one of the original papers on this by Giulio Gubitozzi and others, there was a similar calculation, but the covariant action that they got at was not Horndeski. So it wasn't guaranteed to be sort of stable. And this was also done in a slightly different way, but we'll come to that. But anyway, we have lambda, gamma, m2 to the 4, m bar 1 cube. So this one. So given a particular parameterization, with either, if you want to say your alpha b is a function of the dark energy density, for example, over time, plug this into here, and you see at the level of the background and linear perturbations, what Horndeski theory would give you that particular alpha. These are the forms, these are are the forms of the delta G2s. So essentially, I mean, it's if you're familiar with this stuff, it's fairly straightforward. 1 plus x of m star to the fourth. If you put that back into the unitary gauge from this thing here, it's essentially inverting this. So 1 plus x over m star to the fourth. Maybe I got it something wrong there, but this will become delta g naught to the n, and because n is greater than 2, this, once you add this on, it will not affect your linear theory. You have to go from greater than 3 for delta G4 and 5, because in the unitary gauge, when you put G4 and G5 into the unitary gauge, you have derivatives of G4 with respect to x. So bring down a few powers here. But essentially, these are completely free functions of phi, and you have a lot of freedom here to move between different theories. But if we're just talking about the level of if we're just talking about the background and the linear perturbations, it is defined in terms of the EFT functions. So, I mean, just to give a quick sketch of this is a fairly trivial example, but this is essentially the correspondence. Notice that this did rely on setting phi equal to t, because normally down here in the unitary gauge you'll have phi dot squared, which, because we've chosen that particular foliation, this just becomes a constant. So this is now has no more t dependence. But anyway, so starting from this background and first order action with the delta G naught, making this correspondence, plugging it in, you essentially get out this quintessence model, which isn't in particularly canonical form, but if you perform a field redefinition, you can make it canonical, and so you just have a factor of -1/2 out the front here. Anyway, that one's fairly trivial. It gets more complicated when you go up into G3 and G4. I've sketched the derivation for G3. I haven't done for G4, so limited on time. But anyway, this also is a part of the degeneracy involved in these types of calculations. But anyway, if you start from a term which is x to the n box phi, you could choose whatever term like that you wanted. But for the purposes of simplicity, choose n equal to 1. And in the unitary gauge, look at one of Filippo's papers or something. You can expand this out, and you get something like this up to second order in the perturbations. Okay. Now, if I take every term apart from this one, and so this one, this one, this one, and this one, and move it to the left-hand side, and then make a substitution of delta G naught to be 1 plus x, and then 1 plus x over m star to the fourth, expand it all out, what you're left with by definition is a theory that looks like this, which, when put back into the unitary gauge, you will only get this term out. It's just by construction. In principle, I guess you could go to higher and higher order, but yeah. So this is, in terms of your EFT functions, this is what you get. So you have your x box phi term there. You have some kind of potential term, then x squared and x. And you can do a similar thing if you start from the x squared box phi, or you can do combinations thereof or whatever. But yeah. As long as you get this term out here, you can see there's a particular covariant. There's a theory that corresponds to that, that reduces down. Okay, so just to kind of show an example of this, say for example, EFT functions are measured each to be proportional to, say, the Hubble parameter in this particular way, and omega t is measured to be some kind of decaying exponential. Plug that into the reconstruction, and you get this sort of well-known model of inflation when you identify this lambda here. So yeah, it's a way to go from each of these EFT things to your sort of covariant theory. So I've gone very quickly. I shouldn't have gone over that's a good thing. But anyway. So I'll just say a little bit about this. So further applications If, for example, the speed of gravitational waves was measured to be very close to the speed of light, so you can say alpha t equal to 0. From the inversion, you can say that this parameter here must be equal to 0, and bar squared. It's just essentially this is equal to alpha. Plugging that into the reconstruction, you find that this C1 term here must be equal to 0. No, it was C1. C1 was in G4, so it was C1x in G4. So essentially, this is your in G4x, this is your x dependence in G4. So you can say that on linear scales, this G4x must just be a function of phi. Okay. I'm more or less going to finish up now. This next slide is very, very preliminary. Last Friday afternoon, but this is a proof of principle rather than so maybe don't take this too seriously. But essentially, what you can do is you pick a parameterization, say alpha IPT. So this is from Bellini last year, and from that paper you can take observational constraints. And you can pick values within those observational constraints that also are stable. So believe me that I've checked this. CS squared, CT squared is equal to both positive and the alpha parameter as well. Plug this particular parameterization into the reconstruction, and you find a particular functional form of the potential. I'm not entirely convinced that, putting this all on the same graph I'm not too sure about, because these will all have different units, but I've done this I've set basically m star equal to 1. So this is why there's no this thing here. But essentially, put this here, and then this is your potential with this particular parameterization, and then you each have each other term in your Horndeski function. So this is kind of the other way. Given a particular parameterization, what can you say about the space of Horndeski models that corresponds to? So this is essentially the summary. IPhT is a good way to explore parameter space, but if you can find a way to go back from what we've done, is sort of go back from the space of IPhT onto the space of, say, covariant theories in terms of a potential. What do the different parameterizations of the IPhT functions actually correspond to in terms of your theories? A few other applications we're working on, are they guaranteed to even have an Einstein gravity limit? If you pick a particular IPhT parameterization, is your theory that you're actually describing with that screenable? And I guess long term, I should say from data, because I guess with the reconstruction you can do this. But given this mu and gamma, what can you say about this, rather than starting from here and computing mu and gamma? Okay, so that's essentially the idea. But anyway, thank you.
Hi. Is it working? It's working. So, I mean, essentially, as far as I understand, you've started from some. You have your m's at some initial time t, and at that point you map it to some phi equal to, I don't know, 0, 1, whatever, and then you integrate some equations to get back a solution. But now the question that you haven't asked is, how generic is that solution? So you've reconstructed these models, but if I now move by a small amount away from the initial condition that you've defined, do I still get back something that looks the same as a solution in terms of the m's or not?
I'm struggling to.
So really, I mean, if you were starting from an action, what you want to do is to find some generic solution, some kind of attractor or something like that, where you'd be able to say about the generic properties of the solution, and those would then give you the particular behavior that you're trying to imitate. But you've reconstructed a single solution. So yes, if I start from phi equal to 0, for example, and phi dot equal to 0 at some initial time, then this solution will look in the way that will give you the m's that you have. But if I now start with a slightly different position initially, slightly different velocity initially, some small perturbation, do I get back anything that looks similar? Do I get back something that is very different?
I'm not entirely sure I understand the question.
But
we'll talk about it afterwards. But yeah, I mean,
these are very specific solutions that you've picked in your model space.
Well, what solutions are you talking about?
I mean, the solution for m of t that you get from this model is that solution given some initial conditions on phi.
You're talking about this, or?
No. I'm talking about. You start with some solution, which is your EFT parameters. It's a function of time.
So okay, right? Yeah. Sorry, yeah,
right?
okay, yeah. No,
so now you want to reconstruct the model.
Yeah, sure.
But the question is now: is this a generic solution of that model?
So if you pick, yeah, I mean it's constructed. I mean that's.
Is that one solution?
Yes, but then the point is, if you have what we were talking about before, you have alpha of t parameterized in some sense anyway, to give you behavior which is close to say, for example, omega dark energy as a function of time, because we don't know what underlying theory will give rise to these alpha t's, these alpha parameters. So kind of make a guess which seems reasonably close to what we expect it to be. The trouble with that is that you don't know really what theories you are testing. I mean, there could be some theories that we haven't even thought of yet. So rather than going through every class of models and computing them, it's really saying, okay, potentially we can get some parameterization, some kind of functional parameterization of this in the 10 years time from Euclid or something, to such a high accuracy as a function of time and just saying phenomenologically, rather than starting from a particular model, what kind of potential gives you that background expansion and alphas?
Let's talk afterwards, because I think
maybe we're not talking about the same thing. Okay, fine.